Hey everyone, I'm Neil, your Bio 31 SI leader for this semester, and this video is the first in a series of videos I plan to do this semester, breaking down some of the more challenging concepts of Bio 31, or maybe some of the concepts that students tend to commonly struggle with in this class. And today's video is going to be all about breaking down Hardy-Weinberg equilibrium problems, not just how to solve them, like getting to the answer, because I'm sure a lot of you can just work through the math on your own just fine, but also how to pick through the information in a question efficiently, make sure that you know where you're starting from and where you're ending, and making sure that you are going through a question without wasting too much time, because this is something that costs students a lot of time on exams. They just get drowned in Hardy-Weinberg equilibrium problems, and they spend far too much time on that, and then they lose a lot of time on other questions, and they're not able to give them the right amount of attention that they deserve. So hopefully after this video, you'll get a little bit of a sense of what you should be doing with Hardy-Weinberg equilibrium problems, and you can get on your own way with some practice and make sure that you are tackling these questions in a confident manner. So before we get this started, please just make sure that you have a calculator near you. You're going to want to use it for the question that I have prepared for today. So let me share my screen and we can go ahead and get started. All right, so obviously on the screen here, you see a prompt. This is a problem that I created, and for the purpose of this video, we're going to be going through this problem and working through it together. Now, obviously, I do encourage that you try and do a lot of the work on your own, and if you can solve it on your own, that's even better. So if you do feel like doing that, please feel free to pause the video wherever necessary so that you can catch up on your own time. All right, well, let's dive into it. I'm just going to read out the prompt and then we'll start breaking down the problem. So, you are an oceanic zoologist studying a population of clownfish at a coral reef and sea anemone system. In this population, most fish have fins of equal size. However, a small minority have one fin that is slightly smaller, and you call this phenotype the Nemo trait. There are no intermediate traits, and you confirm that fish with the heterozygous genotype also have two fins of equal size. If you know that this population is comprised of 100 clownfish and that the Nemo phenotype is displayed by 16 of them, how many dominant alleles contribute to the heterozygous genotype in the entire population? So that's the full prompt. Once again, I encourage you to pause the video if you need to, just to solve it on your own. But without further ado, why don't we go ahead and get started into how I think it's best to break down the Hardy-Weinberg equilibrium problems that you'll face in the Unit 1 exam. Now, obviously, for the video, I'll be doing a much slower approach so that you all can follow along, but the idea is that the methodology that I'll be using is the one that you should be implementing, and you should be practicing it a lot so that you can get through these problems at a much faster pace. But just to start out with, I want to mention the way I like to break down Hardy-Weinberg equilibrium problems, and it's sort of a three-step process. The first step is identifying what does the problem want us to solve. And this question is a lot more important than you think. You might think it's pretty obvious. You read a question and you obviously know what the problem wants you to solve, but some students read the question, they kind of skim it or glaze it, and then they come to an answer at the end after doing Hardy-Weinberg equilibrium and using the equations. And it's usually an answer that is correct in the context of the problem, but it might not be the exact answer that the problem is looking for. So let's say the problem is asking for a number of individuals and you give a proportion. Obviously, that's not correct. So you want to make sure that you're solving each problem fully, and the way to do that is to know what the problem wants you to solve for. All right, the second step that you want to jump into is what information does the problem provide? This is another really important step, not because you won't be able to identify what information is given by the problem, but more specifically, some problems can give you extra information like fluff or, waste. It's extra stuff that you don't really need to actually solve your problem. And you want to get all the useless junk out of the way so that you can really get to the heart of the content and start solving the problem. So, what information does the problem provide in the sense that what information is going to be useful to you or relevant to you in this situation? And of course, the last step is connecting the dots. So, in this case, it's connecting between one and two, connecting the information that the problem provides to the answer that the problem wants us to solve for. So, it's a one, two, three sort of process. All right, so now we're going to go through the problem. If you haven't started solving already, please try and implement this three-step process for breaking down this problem. And I'm just going to get this out of here and clear up as much space as possible. All right, so looking at this prompt, we're going to start with step one, which was what does the problem want us to solve? In this case, it's pretty obvious, and in most problems, it will be the last phrase of the actual question. So we can just highlight that here. What they want us to solve is how many dominant alleles contribute to the heterozygous genotype in the entire population. So we're really looking for dominant alleles tied to the heterozygous genotype. All right. So we've got that out of the way. Then the next thing that we want to do is do step number two, which is figuring out what information is provided to us that is really important. So numerically, the first things that stand out to me are that this population is comprised of 100 clownfish, and that the Nemo phenotype is displayed by 16 of them. So these are right off the bat the raw numbers that we're going to be working with, and those both seem to be pretty important in figuring out how to get to our dominant allele number from the heterozygous genotype. Also, maybe some other pieces of information that are important to note but are not necessarily numerical and might help you, you know, create a framework for solving this Hardy-Weinberg equilibrium problem is that most fish have fins of equal size. So that sounds like the dominant genotype, fins of equal size. And a small minority have one fin that is slightly smaller. And you call this phenotype the Nemo trait. So once again, now we have the recessive genotype, which is this minority that have one fin that's slightly smaller and one fin that's normal size. And we're also classifying this phenotype as the Nemo trait, and that's referenced in the actual information that's numerical, that the Nemo phenotype is displayed by 16 of these fish. And so genotype, phenotype, that distinction can be important um, if we're getting into some nuanced stuff. So let's look. Well, there are no intermediate traits. So there's no traits in between having the Nemo trait and having the fins of equal size. So we're going to assume that there are two traits that show up, or like two phenotypes. But again, even if you have two phenotypes, you're still going to have three genotypes. And so we confirm that the heterozygous genotype also has two fins of equal size. So the dominant allele takes focus, whether it's homozygous dominant or heterozygous dominant, to create the phenotype of two fins of equal size. So two genotypes equals one phenotype. And for the recessive, one genotype equals one phenotype. Okay, so this can feel like a lot of information, but why don't we start breaking down that information into our variables so we can more easily track everything that's going on. So let's start with actually just making variables to represent each genotype. I think that's a good place to start. So why don't we say, or actually let's start with alleles, and then we can go to genotypes. So let's say that since this is a trait about fins, why don't we make a big F equal the dominant allele, and we can make little f equal the recessive allele. And so if we're looking at genotypes, that would translate to big F equals, you know, dominant homozygous, big F equals dominant heterozygous, and little f equals recessive homozygous. Okay? So this is how we are plugging in our variables and distinctions into our actual Hardy-Weinberg equilibrium equations, which just as a reminder, and I have this on another slide, um, this is sort of a layout of all the important pieces of information just at a baseline that you will use in Hardy-Weinberg equilibrium problems generally. I've introduced this in my SI sessions, and I think it's a really good resource if you want to sift through all the information and make sure that you understand everything. So go ahead, freeze frame this screen if you need to reference that. But we're just going to go back to our main slide and start working through our problem now that we have some variables set aside. So, I think the first thing that we can really clue in on here with our numbers is that the Nemo phenotype is displayed by 16 of the fish in this population. So what that would translate to in terms of genotypes is the recessive homozygous genotype. So we're going to say that if we use the p squared plus 2pq plus q squared equals 1 equation, and I'll just stretch that out, and we plug in the variables that we came up with. So big F squared plus 2pq, or sorry, 2 big F, and then little f plus little f squared equals 1. That's what our equation looks like. And now we can plug in for f squared, not 16, because 16 is the number of individuals who display the phenotype, but we have to display the proportion or the frequency. And we know this population is comprised of 100 clownfish, so 16 divided by 100 equals 0.16. That's what the proportion would be. So let's just do that real quick. We'll rewrite this and now plug in a 0.16 for that f squared. Okay, so we've kind of plugged in our important information. Now we want to figure out what this is. And it's going to be really hard to get to this actual variable just by using this equation. So what I'm going to do is I'm going to bring in our other Hardy-Weinberg equilibrium equation, which is P plus Q equals 1. And I'm going to use that to find P. So in this case, big F plus little f equals 1. To get little f from f squared, we are going to take the square root of f squared. So in this case, the square root of 0.16. I'm going to do that on my calculator real quick. And you should do the same. The square root of 0.16 equals 0.4. So we have this big F plus 0.4 equals 1. We're going to solve for F by subtracting 0.4 from both sides. And that gives us big F equals 0.6. Okay, so now what do we do? Once again, we want to solve for this big F here. And the only way we can really solve for this big F here is if we figure out this whole little bit, which is that heterozygous genotype. So the way we can do this is by substituting our big F frequency and our little f frequency that we just figured out from using the P plus Q equals 1 equation. So what we can do is 2 times big F, or 0.6, and times little f, 0.4, equals, let's figure out what that equals. And I did it on my calculator. That got me a proportion of 0.48. So 0.48 is the proportion of individuals in the population who have that heterozygous genotype. Okay? And that is also still the equal size fin phenotype. Now we have to convert that into a number of alleles. And the way I would do this is I would convert this proportion into a number of individuals, and then I would convert that into number of alleles. And the reason for this being because I know the exchange rate between individuals and alleles. For every one individual, you're going to have two alleles because that's what each genotype characterizes, right? Each genotype, big F, big F, big F, or little f, translates to the actual individual. So that being the case, I would multiply 0.48 times 100 because there are 100 individuals in the population, right? And that equals 48 individuals with the heterozygous genotype. And then what I'm going to do is I'm going to multiply this by the number of alleles in the population, which since there are 100 individuals in the population, um, or since there is a conversion ratio of one individual to two alleles, I'm going to multiply this number times two. So let me just start another box because it's getting a little cluttered here. So 48 times 2 is to get the number of alleles. And that equals, let me just get that again, 96 alleles. So cool. We have an amount of alleles, and it seems like we've solved this problem. Except, wait a minute, that's not quite right because these 96 alleles aren't just the dominant alleles that contribute to the heterozygous genotype, right? They are made up of the dominant alleles and the recessive alleles that make up this genotype right here, this little f as well. So we're considering big F and little f in this number. And we just want big F. And so since we know that big F contributes half to these heterozygous alleles, because, right, um, it makes up half of that, and little f contributes half as well, we can just divide this number by 2 to get the number of dominant alleles that make up this heterozygous genotype. So I'm going to do 96 divided by 2 equals 48 dominant alleles for the heterozygous genotype. All right. And got a typo there. And that's how you solve this problem. So I hope you were able to follow along with the step-by-step process. I hope you were also maybe able to attempt this on your own. Compare whether or not this was a more efficient, way to solve it compared to your own work as opposed to you doing it. Do you think obviously without the me whole explaining everything in between slowing us down, do you think this process would have helped you solve everything in a short amount of time? And could you follow along with the logical process of getting from the information that we had to the information that we wanted to solve for? Those are all really important questions that you need to ask yourself when practicing Hardy-Weinberg equilibrium. If you are confidently able to do all of the things that I'm sort of putting out here on the screen, then I think you'll be in a good spot and you don't really have anything to worry about. So just keep those in mind and keep up your practice. Don't slack off on Hardy-Weinberg equilibrium because even if you're confident now, if you're rusty on it by the time the exam rolls around, it will cost you both in time and potentially in mistakes. So that's just some advice. But I hope you enjoyed this video and please leave a comment on the video or email me if you have any questions or concerns, and I'll try and respond as quickly as possible. All right, take care.